Good morning everyone. So welcome to the lecture series of VLSI technology with the subject code KEC 053. So in the last class we have covered in the last few lectures we have covered about the epitaxial process, that how the epitaxy is done, what are the types of epitaxy, how we can grow the epitaxial layer, and how the evaluation of those epitaxial layer is done, that is by liquid phase epitaxy, vapor phase epitaxy and molecular beam epitaxy. So with the help of those three process we can have the epitaxial layer which act as a buried layer for the IC fabrication technology. So in this lecture we will start with the oxidation process, that what basically is oxidation, what is the need of oxidation and how this oxidation is taken place. So what basically is oxidation? Your oxidation is a process which converts silicon on the wafer into the silicon dioxide. And for an effective oxidation rate, what we do actually is we will put the silicon wafer into the furnace, and we will provide some water vapors or oxygen, and we will increase the temperature, and with the help of reactions we will have the silicon dioxide layer which will be grown over the silicon, which act as a high quality insulator or mask for the ion implantation or next fabrication steps. So what we are going in this oxidation is, we have this silicon substrate, right, and we have to grow the oxide layer over this. So this we can done by either by using oxygen or by using water wafers. Yeah, we have the silicon substrate and we have this silicon dioxide. So we are going to grow the silicon dioxide layer with the help of this oxidation process. So why this oxidation is required? Because we know that in case of IC fabrication technology, we have to fabricate n number of MOSFETs on a single wafer. So it acts as a diffusion mask which permits the selective diffusion into the silicon wafer, right? So in the last slide I have drawn the diagram that we have this substrate, right? We have this substrate and we have this silicon dioxide, right? And if you need to fabricate the MOSFET, what is the actual structure? We have this N plus doping. We have the N plus doping. Over this, we have the oxide layer and then the gate material, right? So this oxide layer will protect the complete wafer, and then because this doping is done only the selective area, so this oxide layer will protect the rest of the wafer from the from this particular type of doping. So this act as a diffusion mask so that we can protect the window, so that we can protect the complete wafer. We will create these windows and your doping will be done. So next, it is used for the surface passivation, which is nothing but creating a protective layer of SiO2 on the silicon wafer, which is used to protect the wafer from the moisture or any other contamination which is present in the furnace or in the environment. Next, it acts as an insulator on the wafer surface. It is not water, it is wafer surface. It acts as an insulator so that any current from gate, it should not pass towards the substrate. So it acts as a insulator. SiO2 acts as an active gate electrode in the MOS devices structure. It is used to isolate one device from another device, because we are fabricating n number of devices. For example, this is one MOSFET. So after that we will grow the oxide layer, which is known as field oxide, which is used to protect the one MOSFET from the another MOSFET, so that the characteristics of one MOSFET should not interfere the characteristics of another MOSFET. It provides the electrical isolation of multi-level metallization used in the VLSI technology. So now how this reaction is carried out? we know that this it reacts with oxygen. Your silicon will react with oxygen to form the SiO2. Now this SiO2 is not taken from the outside, it will be consumed from the silicon wafer itself, and then the oxide will be grown. So because it is consuming the silicon wafer, so that is why some part of the oxide will be grown inside the wafer and some will be grown outside the wafer. So we can see in this diagram that we have the silicon substrate. This is the, up to this we have the silicon substrate, and we can see that some part of SiO2 is grown inside the substrate and some part of SiO2 is grown outside the substrate. So this to grow the SiO2 layer, this silicon, the process will consume the silicon from the silicon substrate itself. So how much part is grown inside the substrate and how much will be the grown outside the substrate, this will be calculated with the help of molecular weight of silicon and oxygen. We know that molecular weight of silicon is 28 and oxygen is 16. So if you put that in the equation, you will have 28 plus 32, that is 60. So we can say that 60 gram of silicon oxide will be formed by consuming 28 grams of silicon, right? So 60 gram of silicon dioxide will be formed by consuming 28 gram of silicon. So this 60 gram of silicon dioxide, it is the volume into density, that how much will be the volume of this layer and how much is the density of oxides. So then this volume we can write it as area into thickness. So if you write it in terms of area into thickness, this is going to be the weight of silicon dioxide. So area, we can write it as area into thickness of oxide layer into permittivity of silicon dioxide, right? So area into thickness of oxide into multiplied by permittivity of silicon dioxide, this will give you the weight of the silicon dioxide. So in other words, we can write it as TOX will be equal to 60 grams. 60 grams silicon dioxide is grown over the this much area. So we can further convert it into 60 divided by area into 2.27, where 2.27 is the density of silicon dioxide. Similarly, we can write the same equation by for the silicon. Here we write the equation for silicon dioxide, thickness of oxide, and now if you write the equation for the thickness of silicon, it will be 28 divided by area into 2.33, where 2.33 is the density of the silicon. So by using these two equations, we can calculate thickness of silicon divided by thickness of this oxide layer. We will have 28 divided by this factor and A into 2.27 divided by 60. If you solve this, you will have 0.45. So this 0.45 states that if 100,000 Armstrong of silicon dioxide is grown over the silicon substrate, then it will consume 450 Armstrong of silicon. Okay, so that is why in this diagram I have written this 450 Armstrong is consumed by the process. It consumed 450 Armstrong silicon and 550 will be grown over the substrate. So next is kinetics of oxidation. In VLSI, the most important type of oxidation is your thermal oxidation. The principle of thermal oxidation is simple. It takes the silicon sample, we take the silicon sample, put it inside the furnace, we will increase the temperature and will provide the oxidation species, that is your oxygen or water vapors, and your silicon will react either with oxygen or with water to form the silicon dioxide. Now if your silicon is reacted with the water to form silicon dioxide, it is known as wet oxidation. So by this equation, we can see that silicon is reacted with water particles and we will have silicon dioxide plus hydrogen as a residual. So if your silicon is reacted with the oxygen to form the SiO2, to form the SiO2 layer, silicon dioxide, it is known as dry oxidation. So we can have the equation silicon when reacted with oxygen, we will have the silicon dioxide. So during the thermal oxidation process, the oxidizing species move inside through the oxide layer, react with the silicon at this interface, and this is known as the thermal oxidation process. So in terms of quality, the dry oxidation is much more better than the wet oxidation, because in case of dry oxidation, the growth process is very much slower as compared to the wet oxidation growth. And if you need to have thick oxide layer, your wet oxidation method is preferred because of the high growth rate. Anodic oxide is formed in gaseous or liquid medium by electric field, which is introduced which is used to introduce the transportation of the mobile ions, and this method is known as low pressure chemical vapor deposition, LPCVD. And the other methods are, so at low temperature, we can have the temperature range 400 to 500 degrees C. This CVD process uses the saline as a material, and it is reacted with the oxygen at high temperature, that is 1000 degrees C, to deposit the silicon tetrachloride with the carbon dioxide, oxygen and water vapors. So we can see here that the saline is reacted with the oxygen so that we can have the silicon dioxide and hydrogen. So at this point, it is we must note here that there is another passivation film in this silicon substrate, and which is the silicon nitride, Si3N4 film. This film is also used to passivate the semiconductor device, because it acts as a barrier to the diffusion of metal ions, and particularly used to protect the IC from the sodium ions. So reactive sputtering of ammonia or nitrogen is the most common way to deposit this type of film. So in these reactions, we can see here that how your device is how the silane material is used to form the silicon nitride layer, which is used to protect the wafer from the metal ions. Now this thermal oxidation has the advantage because the original surface is, because we know that your original surface is the source of all the contamination, and in case of thermal oxidation, all this contamination will be remain in the outside, and we have the layer of oxide layer below that, which is free from the contamination. That is why this thermal oxidation is used as a gate oxide, because that is where the interface qualities are of primary important, and this is the reason why your thermal oxidation gives you the best quality oxide. So let us study how the species are being transported and what is happening during this oxidation process. So the kinetics of oxidation is predicted by Deal and Grove, and it is invented 30 years ago and is published in a Journal of Applied Physics in 1965. And till now we are using the same model to grow the oxide layer. Because the quality of this model and the result which we are getting from this model is very much accurate and precise. So this model is generally valid for the temperature range between 700 to 1300 degrees C, with the partial pressure of 0.2 to 1 atmosphere, and it is used to grow the thickness of 30 nanometer to 2000 nanometer for oxide and water as a ambient. So what happens in this Deal-Grove model method? We have the gas phase, we have the oxide layer, and we have the silicon wafer. So this model divides the complete structure. Here we have the silicon substrate, we have the substrate, then we have some oxide, okay, and here your gases will be passed to grow more oxide layer. So we have the gas area, gas region, oxide and silicon, okay. So we have oxide and silicon. So in this case, we have the three flux value, that how these values are converted into one point to another point. So this is perfectly generalized situation when your silicon is getting oxidized. So first of all, we have the oxidizing species in the gas form, right? We have some gas which will be reacted with the silicon so that your oxide layer can be formed. So from the gas stream, it must be transferred to the oxide layer. Here in the diagram, we can see that from this gas, it is transferred to this oxide layer. So once this oxidizing species have reached the oxide gas interface, it must diffuse. These gas elements will diffuse at this point, and then they will enter into the silicon dioxide area. Then the oxidation take place by the movement inside the oxidizing species. So if they want to react with the silicon, they must move through the oxide layer, right? So once they are settled here, they if they want to react with the silicon, they will move towards the silicon area, and then they will combine at this silicon and silicon dioxide interface, and finally your oxidation will take place. So lastly, once this oxidizing species reaches the silicon dioxide interface, it must react with the silicon. So now we have the three movements. In the previous diagram, we can conclude that we can have three movements. The first movement is when the oxidizing species from the gas stream to the oxide gas interface, right? Next is the movement of oxidizing species through the existing silicon dioxide layer, right? So we have this, right? We have this gas, oxide and silicon. So first one is when they are settling here, second one is when they are traveling through this, and the third one is the reaction of oxidizing species at the silicon dioxide interface. So when they are traveling up to this level, they will react here, the silicon present. So for all three areas, we are going to have the three flux equations, F1, F2 and F3. So before writing the flux equation, let us get to know about these parameters, that what are these parameters, that is your Cg, Cs, D, C0 and Ci. So Cg, that is the concentration of oxidizing species in the bulk of the gas. Cs is the concentration of oxidizing species right next to the gas oxide interface. C0 is the oxidizing species in the outer oxide surface. Ci is the oxidizing species at the inner surface, and C star is defined as the equilibrium concentration of oxidizing species in the oxide layer. So F1 is the flux of the oxidizing species in the bulk of gas. So from the bulk of the gas right next to the oxide layer, we can write this flux 1 is equal to Hg Cg minus Cs, where Hg is the gas phase mass transfer coefficient, some proportionality constant is there. So by gas law, we can replace this Cg and Cs by the partial pressure of these oxidizing species by the formula PV is equal to KT. So we can write F1 is equal to Hg divided by KT, Pg minus Ps. We name this as equation 1, or let us not write it as 1. So according to Henry law, that in the equilibrium state, the concentration of species within the solid is proportional to the partial pressure, that is the species in the surrounding gas. Okay, so it states that the as per the Henry's law, the equilibrium of concentration of a species within a solid is proportional to the partial pressure around that solid in the gaseous form. So we can write it as the C star equilibrium constant concentration, which will be equal to H into Pg. C naught, similarly C naught will be equal to H into Ps. Substitute these values in this equation. We can write it as F1 is equal to Hg divided by Hkt C star minus C naught. So let us write this at equation 1. So F1 is proportional to the equilibrium concentration of the oxidizing species and the concentration of the oxidizing species at the outer surface. So it is proportional to the difference of this equilibrium and the outer surface. So next we have the F2, that is when your oxidizing species travel from gas oxide interface towards the silicon dioxide and silicon interface. So we write it as D C naught minus Ci divided by X. Oxidizing species move through the oxidizing layer because of the concentration gradient, and it is diffusing across the existing oxide layer, and the diffusion is always proportional to the concentration gradient, that is D. Next, the F3 is related to the reaction of silicon with the oxidizing species. Now, because we have the abundance of silicon at the silicon substrate, so more reaction will be there. So we can directly write it as K3. So write it as equation 2, and we have the equation 3. So F3 we can write it as Ks into Ci, because this flux is directly proportional to the concentration of silicon which is abundant at the silicon wafer. So we have these three flux equation, and under this under the steady state condition, all the flux values will be equal. So if we equate F2 and F3, we will have this equation D C naught minus Ci divided by X is equal to Ks Ci. So we can rearrange this equation to form Ci is equal to C naught divided by 1 plus Ks X divided by D. Now this equation relates the concentration of oxidizing species in the inner surface with the concentration of oxidizing species in the outer surface, right? So this equation relates the concentration of inner surface to the concentration of outer surface. So if the value of X is very small, a very thin oxide layer will be there, and then Ci is going to be nearly equal to C naught. So substitute the value of Ci for this equation F3. Substitute the value of Ci and equate F1, F2 and F3. We will have this equation C naught is equal to C equilibrium concentration 1 plus Ks X divided by D, in denominator 1 plus Ks divided by H plus Ks X divided by D. So from the above equation, from this equation we can state that C naught in terms of equilibrium concentration C star. Your outer concentration is in the form of C equilibrium concentration. Ks is the reaction constant, H is the gas phase mass transfer coefficient, capital H is the Henry constant if you put together, D is the diffusion coefficient, X is the existing oxide layer thickness. Now if you look at the equation, Ci is equal to C naught divided by 1 plus Ks X divided by D. If we put this equation in the equation 6, we are going to find Ci. This Ci will be equal to this factor and C naught is this. Now we can have n number of cases that if this value of D approaches to 0, if it is approaches to 1 and if it is approaches to infinity. So that we are going to cover in the next few lectures. So for example, if your D approaches to 0, then the denominator, this denominator will be very large and Ci will be very small. So this Ci tends to 0 and this Ci will be equal to C equilibrium. So that is all for today, today's lecture. In the next few classes, we are going to cover that how the value of D can be varied from 0 to 1 to infinity. so that we can have a precise layer of thickness of oxide layer. And so in the next few lecture we are going to see the practical examples that how we can use this deal groove model method to grow the oxide layer and to calculate the thickness of oxide layer. So in today's lecture we get to know about the oxidation, what is oxidation, how this oxidation process is carried out, and how, which type of oxidation is better, and how this deal and groove model method is used to calculate the kinetics behind the oxidation. So that is all for today's lecture. Thank you so much.